Welcome, everyone. Thank you for tuning in. I'm very pleased to welcome you all to what is now our fifth webinar in the Rain Enhancement Hub series, hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science. My name is Yusuf Webby. I'm a program officer for the UAE REP, and I'll be moderating today's webinar. During the course of our last four webinars, we've been breaking down the complex processes involved in rainfall enhancement research and discussing the emerging challenges as well as the latest developments in the field. Aerosol cloud precipitation interactions is a long-standing research area that is yet to be fully understood. Aerosol particles are key components of the atmosphere and have multi-scale impacts on Earth's climate and hydrological cycle. As such, in addition to an in-depth understanding of the local meteorology, cloud seeding programs require an accurate characterization of the background dust and aerosol populations and their potential role as natural seeding particles. This is particularly relevant to the Arabian Peninsula region as a hotspot for atmospheric dust covering a wide spectrum of physical and chemical properties. Joining us today to learn more about the direct and indirect effects of dust on clouds and precipitation over the Red Sea coast is Dr. Sagar Parajuli, a research scientist from King Abdullah University of Science and Technology in Saudi Arabia. Dr. Sagar is a self-motivated researcher in the areas of regional and global climate modeling, air quality modeling, as well as big data analytics. His current research focuses on natural and anthropogenic aerosols using satellite and ground-based observations, field measurements, and numerical modeling to improve their characterization in regional climate models. We're very fortunate to have him present for us today on this topic. Audience, please go ahead and type in your questions at any time during the webinar using the chat box to your right. We'll be sure to address your questions during the Q&A session. For now, I'm handing over to Dr. Sagar.
Thank you, Yusuf. Thank you for this nice introduction. Yeah, so I feel very good to be back to Abu Dhabi, UAE, because I did my master's there. I have a strong connection there. And so today's talk will be about the direct and indirect effect of dust on rainfall. Yusuf, can you see my screen? So the topic is direct and indirect effect of dust on rainfall. So to be more specific, I'll be talking about the effect of dust on rainfall over the Red Sea coast using WRF-Chem simulations. I'm not sure if I'm sharing my screen correctly. Okay, I think it's fine. I'm sorry about this. Okay. Okay, so let's begin today's talk. So in 1880, John Aitken did a simple experiment at his own homeland. He passed the vapor coming from a boiler to a glass jar with and without a cotton filter in between. This simple experiment, which showed formation of cloud droplets with dirty air, laid the foundation for research on aerosol climate interaction. Today, the finest aerosol mode, which is less than 0.1 micron, is called Aitken mode after his name. You can clearly see in this picture there are different aerosol modes, and the finest mode is called Aitken mode. Well, although John Aitken was referring to any atmospheric aerosol particles as dust at that time, the climatic and environmental implications of mineral dust is now well established. Measurement in high cirrus clouds show that mineral dust dominantly forms ice nuclei. So we all know now that dust is a very good ice nuclei. And not only this, mineral dust from Sahara and China has been found in rainwater in California, USA, as reported in a science paper. Talking about cloud condensation nuclei or ice nuclei, not only dust, several other atmospheric particles like pollen, sea salt, sulfate, and even bacteria can provide a surface for condensation, thus act as cloud condensation nuclei or ice nuclei. Although dust particles are weakly hydrophilic, they are larger in size compared to other anthropogenic aerosols, and thus they can be activated at a smaller supersaturation compared to other aerosol species. So that is the uh, positive aspect of mineral dust. Well, there has been 150 years of research, as Yusuf mentioned earlier, but the dust-climate interaction continues to baffle scientists. Several papers on these topics are still published in Nature and Science. John Aitken alone published 6 articles on this topic. I'm talking about this 1880s. So this clearly shows the importance of this topic. Now, to be more specific about aerosol indirect effects, the direct effect is understood for a long time. The aerosol effect on climate through aerosol radiation interaction is referred as the aerosol direct effects. Many people know about this. There has been a lot of research on this topic, and it is one of the well understood aspects of aerosol climate interaction. However, the effect of aerosols through clouds, mainly albedo and lifetime, is generally referred as indirect effects. And due to the fine scale features of indirect effects, they can best be realized in cloud resolving scales in regional climate models. And in the beginning, aerosol indirect effects were not considered by climate models, and this is due to their high uncertainty. But today, most CMIP6 models incorporate indirect effects, whereas only a few did in CMIP5. Clearly, if you look at this picture on the right, aerosol indirect effect is as large as the direct effects, although the uncertainty of aerosol cloud interaction is still very high. So, uh, now getting more close to the topic, why study dust effect on rainfall? Well, water is essential for plant and animal life, and rainfall affects the distribution of surface and groundwater resources, uh, which are constantly declining in this region. Irregular rainfall causes floods and droughts, and causes waterborne diseases like malaria and diarrhea. And so this study is particularly important in regions with high atmospheric dust loads, such as MENA. And cloud seeding experiments are being considered in this region, for example, in UAE and Saudi Arabia, to augment the availability of freshwater resources. So the objective of this research was to find a few important research questions. The first one is that, does dust enhance or suppress rainfall? And if it does, what physical mechanisms are responsible for any enhancement or suppression effect? And another question is, how does dust interact with local breeze circulation? Because we are residing here over the Red Sea coast, where breezes are strong, and there is a considerable topography here. Aerosol effects are usually calculated in terms of radiative balance. However, we want to calculate the effect on rainfall amounts because rainfall impacts our lives directly. It is more intuitive to understand. If we only talk about radiative balance, we may not understand its meaning. But talking about rainfall amounts, we understand it better. So this is our WRF-Chem modeling domain. Our domain is located over the Red Sea coast, KAUST campus in the north, and in the south, the domain extends to Ava, which is very well known for high amount of rainfall in Saudi Arabia, and there is a considerable topography here. So this is the our high resolution domain at 1.5 kilometer resolution. We have parent domain D02 and another outermost domain D01 that covers all the important dust source of this region. We do our simulations at a cloud resolving scale, and we carry our simulations for the month of August for 10 years, from 2006 to 2015. We focus on August because sea breezes are particularly strong during this month. We want to get a realistic quantification of dust effect on rainfall. So that's why before doing our calculations, we calibrated the dust amount and size distribution according to the Aeronet observations. And we use one of the most developed aerosol scheme called Mosaic 8-bin sectional aerosol scheme, coupled with a double moment microphysics scheme, and we use boundary conditions from high resolution ECMWF operation analysis with SST updates. So we have two sets of model experiments. The first set here includes both direct and indirect effects. And the second set here on the right includes only the indirect effects. That means in this experiment, we are restricting the aerosol radiation interaction. So we are only going to get the indirect effects. And why we are doing these two sets of simulation? Because we want to calculate the total effect, indirect effect, and direct effect. So when we have these two sets of experiments, we can calculate the direct effect by subtracting these indirect effects from the total effects. And that will give us the direct effects. And in each set of experiments, obviously we have two experiments with all aerosols and another sets with in which we don't include dust. We restrict the emission of dust. So because our purpose is to understand what happens when the dust is included in the model. We use several data sets for validation of our work, radiation data, satellite rainfall data. We also have microphysical measurements from a field campaign in Ava region that occurred in 2009. We use MERA2 data, reanalysis data, this MODIS satellite AOD data, and we also have a dedicated LiDAR to retrieve vertical profile of aerosols here at KAUST. And we have weather station data and we have Aeronet stations. So talking about the rainfall features of the study area. So this picture here shows the section of rainwater mixing ratio in a section that passed through KAUST and through Ava, which observes more rain. So rainfall is actually very much predictable over this region. The daily maximum rainfall occurs exactly at 15 UTC. That's about 6 p.m. in the evening, and at the same place over the mountains, because we have a topography here, and we have sea breezes. The reason why the rainfall is predictable is because the moisture availability is governed by sea breezes, which are a recurring feature. And so talking about the cloud features, diurnal rainfall mainly caused by warm cloud bursts. Here we're talking about warm clouds, not ice clouds. And these clouds are found at a height of 5 to 6 kilometers, mainly altocumulus, altostratus, and deep convective clouds, as revealed by Calypso data. So talking about the model results, so our WRF-Chem model actually reproduces the key features of the rainfall over the study domain quite well. The peaks of rainfall here, let's say, even during the extreme rain events, is reproduced well compared to this IMERG satellite retrieved data, which is 0.1 degree resolution dataset. Not only time series, the spatial distribution of rainfall is also simulated reasonably well by our model. There is a the most rain follows the mountainous terrain, or these are called the Sarawat Mountains. Uh, so the most rainfall occurs over these mountains, and as we can see from both model and IMORG data. And we compare our simulations of aerosol number size distributions with field measurements. We can see here the 8 sectional sizes of aerosols match quite well with the observations. This is a log graph, but there is some difference. But for microphysical observations, there is already very high uncertainty. So these are not very uncommon. And we have here the comparison of model simulated CCN number concentration with the ground measured CCNs. And the results show that if you look at here, CCNs are generally overestimated by a factor of 2. That's again large. Comparison with WRF satellite data. So we compared our simulated CCN number concentrations with WRF satellite data as well. Rosenfeld et al. Developed an algorithm to estimate CCN concentration from WRF satellite data. So talking more about this algorithm, the number of activated CCN in a convective cloud base is a function of cloud drop effective radius, and the cloud base updraft speed is a linear function of cloud base height. So that is how the CCN number concentrations were retrieved, and we compared those estimates with our simulations, and as before, the model overestimates CCN by about a factor of 2 again, just as in previous ground measure observations. So now it raises an important perspective that rainfall amount is well simulated. We saw it, the spatial pattern of rainfall and the temporal pattern of rainfall was well simulated. So now what does it mean to overestimate CCNs is that CCN is not a limiting factor for rain formation in our region, because we already have a lot of aerosols in the atmosphere in this region. So now talking more about the dust effects. So here I'm showing the total effect, indirect effect, and the direct effect on 2-meter air temperature, 10-meter winds, and 2-meter water vapor mixing ratio. As you can see, the total effect is cooling effect, as the blue color shows. The dust causes considerable cooling effect through the direct effect here, that is more reflected in the total effect, and also through indirect effect, it affects the temperature, and dust affects the winds along the coast here, because you'll see the black dots there, which represents statistically significant areas. That means wind were significantly affected in this area. Also, the 2-meter water vapor mixing ratio was also very high here in the over the land. So that means moisture transport was also affected. So to understand the dust direct and indirect effect and more details, we actually analyze the results further by separating rain events into extreme and normal rain events based on the 90th percentile value of domain average daily rainfall, so which was about 1.33 millimeter. Because the processes governing normal rainfall events and extreme rainfall events are very different. So we wanted to understand the physical mechanisms. So for normal rainfall events, the net effect was driven by direct effects, which suppressed rainfall by about minus 5.8%. And indirect effect was opposite in sign and nearly equal in magnitude. And it canceled the direct effect out, causing net rain suppression. Well, for normal rain events, dust effect depends upon local circulation, as I explained before. So dust scatters shortwave radiation, cools the land surface, weakens the breeze circulation, reduces moisture transport to the land, and thus suppresses rainfall. And why positive indirect effect? It's because high dust concentration facilitates raindrops to grow in the presence of sufficient moisture. And for extreme rain events, The net effect of dust was driven by indirect effects. So this is very different, and which enhanced rainfall by about 4.6%. And in this case, actually, the direct effect further enhanced rainfall. Remember, it suppressed the rainfall for the normal rain events. So in this case, direct effect further enhanced rainfall. And the reason is extreme rain events are caused by synoptic features, and positive indirect effect is same as in normal rain events. High dust concentration facilitates raindrops to grow, and positive direct effect is because of the shortwave absorption. So we have a lot of dust, and that is well mixed in the atmosphere, and it causes shortwave absorption, and that actually enhances breeze circulation. So here I'm just summarizing the results of direct and indirect effects here. The direct effect suppresses rainfall for normal rain events, but enhances for extreme rain events through shortwave warming. And thus direct effect depends upon the local circulation, the sea breezes. And indirect effect enhances rainfall for both normal and extreme rain events, regardless of the breeze circulation. This is important. And again, indirect effect is caused by the cloud droplets growth. Um, so broader implications of our research. Dust is often considered an air quality threat. However, our study highlights dust's positive contribution in modulating rain. So now we have to think in a different way, because dust is part of the natural ecosystem. It not only affects the rainfall, it also provides nutrients for the ocean ecosystem. And our study has implications for managing regional water resources. Um, we all know there is a Saudi Green Initiative which plans to plant 10 billion trees by 2030. And of course, understanding of extreme rainfall event is very important to minimize the risk of heavy flooding and loss of public property. So now talking about the cloud seeding perspectives. So our simulations using WRF-Chem shows that it is possible to conduct a realistic model experiment to evaluate the effectiveness of cloud seeding and with WRF-Chem, and it can be a cheaper alternative to more expensive field campaigns. And another important thing that we found is that the presence of background dust is very important to be considered for cloud seeding applications, because we saw that after a certain point, the number of cloud condensation nuclei concentration had no much effect on rainfall. And so summing up all this, cloud seeding efforts can be optimized through targeted model experiments, considering the following factors: the type and height of seeding particles, the intended location of rainfall, presence of deep clouds with high updrafts, and the ease of flight operations. So cloud seeding is actually an optimization problem which needs to consider several factors. So with this, I thank you very much, and this is the end of my presentation, and we'll discuss more about this topic with Yusuf. Um, yeah, I will now hand over to Yusuf.
Thank you very much for the insightful presentation, Dr. Sagar. We do have a few questions from our audience, so we'll tackle them in the next 15 minutes or so. I do want to say you made a pretty bold statement there on proposing modeling as an exclusive alternative to field campaigns, but I'm more of we've also seen this a lot in the program, so I think those go hand in hand. You do need those local scale, micro scale, high resolution observations from aircraft platforms to really validate what you're getting in the models. But I think you'd probably agree with me on that. So the first question is related to the cloud depth. So a critical factor for effective collision coalescence to take place is the available depth of warm cloud, generally 1 kilometer and above. would be sufficient for effective collision coalescence. But what range of cloud depths did you observe in this case study?
Yeah, that's right. So we have over the mountains, actually, we have very deep clouds during strong convection. If you remember, I don't know if you can share, if you're able to see my screen. Are you able to see my screen? So I
Yeah.
showed you, yeah, I showed you here, the the at certain times there are very deep convective clouds, and but I guess that's it depends on where we want to get the rain. So because well, where there are deep convective clouds, there is already rain happening. For example, in Ava, so it's already raining there. We may not want to do cloud seeding there, right? Because we want to do cloud seeding more in the coastal area, and in those area. So I think we have little clouds. We have a very unique situation, high surface evaporation, and I think it again becomes an optimization problem, as I mentioned earlier. Yeah.
Indeed.
Yeah.
The next question is on the chemical properties of the background aerosols. So do you have any information on the chemical properties of the background aerosol population, and how important would you see that to incorporate this that information into the modeling work?
Yes, no, that's very, very important. Actually, I must confess that as of now in WRF-Chem, so in our simulation, we didn't consider the chemical aspect of mineral dust. Dust is usually treated as an inert material, a non-reactive material. Just only it considers the uptake of water. However, I recognize, and there is a possibility. So it is actually, yeah, we plan to do it in the next phase of our work, because mosaic aerosol scheme allows the treatment of different chemical species of dust, calcium carbonate, sodium chloride, and all different constituents. And after that, we'll be able to more accurately determine the seeding fix.
And in terms of cloud-based temperatures, do you have a range that you were targeting in this case study? So,
well, yeah, we have a range of different clouds here, so we can't really say this or that, because yeah. So yeah, there are different range of clouds, and it again depends upon which clouds we want to seed, and at what timing, what seasons. So yeah, there are several factors.
No, so leading into, so my question that I asked that because I was curious about so you mentioned these are warm cloud processes, but I would think maybe compared to the UAE, like here we have a lot of mixed phase, most of them are mixed phase cloud processes as well. So when you mentioned that the direct effects were stronger in the case of the extreme events.
Yes.
So that's the question. So you would think that the stronger updrafts, the cloud depth, and the residence time in the more extreme events would help the dust particles act more as INP. So we've had recent results that have shown that there's a certain degree of ice nucleating particle activity from dust as well.
No, I totally agree with this. Again, WRF-Chem, in talking about WRF-Chem, we didn't consider the ice nucleation properties of dust mineral, because WRF-Chem doesn't allow at the moment, but again we plan to include it. But in our location, so clearly we wanted to understand how the direct and indirect effect compare with each other, and it was a very unique results when we look at the normal rainfall events, because normal rainfall events are recurring rainfall. They have a recurring rainfall pattern over the mountainous region. It almost predictable. However, for extreme rainfall events, so they occur through different synoptic processes, and the effect was quite different. So in this case, aerosol indirect effect was more important, and the dust direct effect was not important. So it's for smaller rainfall processes, the direct effect that occurs through cloud, aerosol, or aerosol radiation interaction is, we have to understand this.
Great. We
Yeah.
have a question from Professor Edward Graham, a good
Hmm.
friend of the program. Do you
Okay.
have any data on very high dust or CCN concentrations, for example, times 10 the usual or greater? And if so, what the effects are?
Well, yeah, we compared our cesium concentrations with observations. Again, our simulation shows very high cesium concentration in the model, but but again, it was not translating into high rainfall amounts because we already had a background aerosols with other anthropogenic aerosols in our model simulations. So we need to redesign our experiments if we want to understand the effect of different size of dust particles on seeding properties. So I can't really say about the, maybe you are referring to the giant CCM properties,
Hmm.
but mosaic aerosol is limited to only 10 micron in diameter. That is the maximum diameter that is considered. So most of the upper sized aerosol are excluded from our results. So that limits our ability to answer that question.
So this leads me to the final question, I think, for this session. So the
Hmm.
aerosol size distribution that you showed from the model and the field observations is very comparable to that we have over the UAE from our aircraft measurements as well.
Okay.
So you see the peak at around zero point 0.1 micron, and then it flattens out towards that 10 micron range and beyond. But
Hmm.
even in terms of the magnitude of the number concentration, it's very comparable as well. So I found that very interesting. But you do
Okay.
make a statement that the cloud growth does not strongly depend on CCNs, unlike in other aerosol limited areas.
Yeah.
Um, but you can argue that, based on Segal's paper, I'm sure you're familiar with Segal et al., the
Hmm.
papers in the early 2000s, on the effect of overseeding. So there's a potential effect from, he reports this optimum seeding concentration. So
Okay.
if you go beyond it, then you see a sort of a negative impact on the collision coalescence process. So that's one thing I wanted to get your opinion on. Do you see any impact of these high concentrations in the small fine aerosol sizes? And what would be the impact of using maybe larger seeding particles, say just focusing on 10 micron size
Okay.
ranges rather than the conventional flares that go from zero point 0.1 out to 10, but having that median of 10 micron, how would you see that impacting? And would that be something interesting for you to simulate maybe in a future study?
Yeah, I know. I think that's a good suggestion, I would say, because yeah, I don't really can. I'm not able to provide insights on this because yeah, we have a very limited size of aerosols in our current simulation. But yeah, I agree. It is going to have an impact because so aerosol. Even talking about aerosol indirect effects, it is very complicated, as you know. So when there are smaller droplets, right? So they when you have high aerosol concentration with the smaller size of particles, the aerosols rise up, right? So more cloud droplets which are lighter, they rise up in the atmosphere and they go to the higher atmosphere and they freeze there and release latent heat and cause ice cold cloud process, as you said before. So it's very complicated, and there is actually already a lot of debates what actually how aerosol affects the rainfall processes because it's very complicated because sometimes we see the small aerosols increasing the rainfall and sometimes it is decreasing, but the fact that we understand now is that in the beginning of a convective process, uh, aerosol suppress rainfall, right? And but when we consider the long term aspect, in the long term the aerosol actually increases rainfall because they increase the cold cloud processes through the this latent heat release. So yeah, I think yeah, it is. There is a lot of open questions on this field, but I can see in the model using WRF-Chem we can explore different, targeted experiments to answer all of these questions.
Indeed, it's a very critical research area, especially for the region.
Yeah,
Here, not much
I totally
studies
agree.
we're looking at.
Yeah.
So I really want to thank you once again, Dr. Sugar. Do you have any questions for me or comments before we wrap up?
No, I think no. Thank you for the invitation. And well, yeah, I know the activities of UAE but yeah, of course. Why don't you share me? I mean, if there are any ongoing, cloud seeding activities set by NCM over the region.
Sure.
Uh,
Sure, we'll be in touch for sure.
yeah.
I just want to thank you again. Very interesting work, and thank you for your time and presenting it. The webinar is recorded and will be available on our website for those who missed the live stream. I encourage you all to attend our next webinar, which we'll advertise on our channels in the near future. Have a nice rest of your day or evening, everybody. Bye-bye.